we still have 5.5 and 6.2 to cover. Can we hold off on homework questions until the review? Is that okay? All right. So, in 5.5 we were talking about the substitution method. And this isn't the only integration technique. It is somewhat limited. If you go on to Calc 2, you'll look at other techniques. So just know this isn't the end-all, be-all. This example here, number 7, and example 8 are kind of similar. When you see something like that's 1 over like a linear type function, you should let your u equal to the bottom. And then what you'll end up with is sort of this logarithmic form. So if we let u equal to 5x, we have to account for the substitution and the derivative of the substitution. So du is 5 dx. But since there's only a dx left in the original integral, our substitution is 1 over u, and we account for the dx. There is no 5 in the original integral, so we move the 5 on the other side with the u. So we have 1/5 du is dx. So this works very similarly to example 7. So 1/5 times the integral of 1 over u du is what we get after our substitution. Which again, you should write this antiderivative with the natural log of the absolute value of u plus c. And then we resubstitute u was 5x. So the antiderivative here is 1/5 natural log absolute value 5x plus c. I guess I did a couple of examples there. I was going to talk about this, the natural log form of antiderivatives, but since we're kind of behind, I'll skip that. If you go on to Calc 2, you will see that. So it's not like we're missing out on anything, but I'm going to skip this for now. It's just a faster technique. It still boils down to a U-substitution. It's just recognizing the pattern. It's a little bit quicker. So this is still the same kind of idea. I'm going to skip that as well. Okay. Example 9, the antiderivative 1 over square root of 1 minus 9x squared. What does that kind of remind us of?
Inverse sine.
The inverse sine. Okay. So I guess there's a couple of ways to approach this. One you saw in section 4.9, and we'll look at that. But how does the U substitution help us here? If we're thinking along the lines of the inverse sine, the antiderivative of 1 over the square root of a squared minus x squared is the inverse sine of x over a plus c. So I guess really the first step is to rewrite so we can maybe see this a little bit more clearly. We're going to express 9x squared as the quantity 3x squared. Okay, so what would our substitution be?
3x.
Right, u equals to 3x, because notice here, we just have a 1x squared. Here, this is 3x squared. So if we let u equal to the 3x, when we resubstitute, we'll have 1 over the square root of 1 minus u squared, not some coefficient in front of it, which means du is 3 dx. Again, no 3 present in the integral involving x, just the dx. So we have to divide by a third, or divide by 3 rather, multiply by a third. So then this, maybe you can see it already, but once we apply the u-substitution, then we have 1/3 integral of 1 over the square root of 1 minus u squared with respect to u. So then we can see that, I think, a little bit more clearly that the antiderivative of 1 over square root of 1 minus u squared is the inverse sine of u. And technically our a is 1, so it's the inverse. If you want to look at it initially as the inverse sine of u over 1, totally fine. Is everybody all right with what we've done here? Are there any questions?
So you got u over 1. How did you get that?
Yeah, so this is our a. 1 is a,
Oh, I see.
because that's the same thing as 1 squared. All right, and then resubstituting, we have 1/3 inverse sine of 3x plus c. So note in the formula from 4.9 with the antiderivative of sine inverse, or sorry, the antiderivative that results in sine inverse, we didn't have a coefficient in front of x. The inverse sine and the inverse cosine were the only ones from that table in 4.9, or the sheet from 4.9 that didn't have the additional factor of the 1 over a in front. But we see here now when we have a coefficient, a linear thing like this, or a coefficient on x, that it does result as that 1 over portion. But that's only if we have this kind of thing here with x. Are there any questions on that? So in 4.9, we could evaluate that without having to substitute. We just had to manipulate it algebraically. So this is maybe an approach we would have taken from section 4.9. Well, thinking back again to the formula in red, we're looking at a 9x squared. If I could have that just as an x squared, then I could apply the formula to that. So what that entails is that we have to factor this 9 out of the denominator and get it out of the root. Okay, so we rewrite this. Under the radical, we're factoring out a 9. So we can just have that as an x squared. So that means the 1 actually has to turn into a 1 over 9. And then in the bottom, since we have the square root of a product, we can take the square root of each individual term multiplied. So here, the 1 over square root of 9 just turns into 1 over 3. And then we have the square root of 1/9 minus x squared, or 1/3 squared minus x squared.
It's just another way you can do it.
Yeah, it's just another way. And I think there were a couple like this in 4.9's homework, if I'm not mistaken. So what we're looking at now is whatever it was called, table 4.9. I don't know what number it was, unless somebody has it offhand, with A equal to 1/3. It was like number 10 or 11 or something. But anyways. And notice this 1/3 right here is the constant. So really that 1/3 is sitting out in front of the integral square root of 1/3 squared minus x squared. Okay, so all of the antiderivative portion, that's what's giving us our inverse sine of x over a. So that's our constant of 1/3, and then the antiderivative here is the inverse sine of x over a. And then, plus some constant here, times. So notice that's the same result. Once we simplify the argument of the inverse sine, it's 1/3 inverse sine of 3x plus 3. Let's see. So just an alternative way to do that. I think perhaps if you look at both methods, maybe the U-substitution is a little bit shorter of a route to get to the result, but nonetheless they both work. And it's not always the case that you can get some algebraic manipulation to work over a U-substitution. Sometimes a U-substitution is the only option.
This would be algebraic way of your saying.
Yeah. Okay. So do y'all have any questions on that? So the thing with U-substitution is a lot of the times once you try a substitution, it may not work, right? I think it's just a matter of practice to determine which U-substitution will work, if anything. But it's not always straightforward like these previous examples. Sometimes you have to manipulate your substitution even further to account for everything present in the original integral. So this is an example of one of those types of problems. First of all, note that if you're confused as to what u should be, or even if it'll work, then maybe you try, let me let u equal to x, then du is dx. But if that's our substitution, then this integral here turns into the integral of u over u minus 2 with respect to u. And so that didn't help any, right? We just turned the x's into u's and it's still the same problem. So at that point we might say, well, let me try the bottom. Let me try to let u equal to x minus 2. Note the derivative of u with respect to x is still 1 dx, so we still have du equals to dx. What's left to account for in the original? What do we have to account for in the original integral? So here, let's write it out. What we have is the antiderivative. Our x minus 2 was u, and dx was du. Right? So that's all we've accounted for. We still have this x sitting on top that we have to account for. Everybody agree with that? Yeah, so how do we do that?
Would be u plus 2 or something.
Yeah. And so we're getting that from the original substitution. Our original substitution says if u is equal to x minus 2, then that implies that u plus 2 is equal to x. So everything we do, manipulating the substitution, taking its derivative, whatever we decide to do with that algebraically is valid, but we're doing all of these things based on the original substitution. So original substitution, solve for x. Original substitution, take the derivative. And so we can put in place of the x up top, u plus 2. Is everybody all right with that? Are there any questions? Now again, there's nothing guaranteeing that this u substitution will work. You have to say, well, this is where I'm at right now. I have u plus 2 over 2. It doesn't look that much different than the original antiderivative or the original integrand. But the advantage of having u plus 2 over u versus x over x minus 2 is what? What can we do with the u integral that we couldn't do with the x integral?
Over u plus 2 over u?
Right, we can split this up. So since we have two things over a single thing, we can split that up into two different pieces. X over x minus 2 cannot be split up into two different pieces. So I'm going to just start here. So we're just going to rewrite that now as the integral. We have u over u plus 2 over u. So that's the advantage. Again, we still don't know that this is going to help us, but maybe from here we can see that it might. And so that simplifies to the antiderivative of 1 plus 2 over u with respect to u. So then we look at that and say, well, can I take the antiderivative of 1 with respect to u? Yeah. Can I take the antiderivative of 2 over u with respect to u? Can I do that? Yeah. So now we have something we can find the antiderivative of. With respect to u, the antiderivative of 1 gives us u. What's the antiderivative of 2 over u?
2 natural log absolute value of u.
Right, that's just the natural log. The 2 is a constant. 2 natural log absolute value of u. I'll write this here. So there's our u plus 2 natural log absolute value of u plus c. And then we can resubstitute u was x minus 2. X minus 2 plus 2 natural log absolute value of x minus 2 plus c. So sometimes you do have to manipulate your original substitution. It's not always make a u substitution, take its derivative, and then it fits perfectly. And often there's antiderivatives where you have to make a u substitution 2 or 3 different times to get it down to something you can find the antiderivative of. We won't see any of that, but it's just to say that this is a limited technique. Does anyone have any questions about that example? And often more than once u substitution will work. So maybe do one of these and then talk about the other one. If you want to try to finish that, we can. Okay, so let's try, let's start out and let u equal to x plus 1. So x over root x plus 1, we're going to let u equal x plus 1. Y'all try to take over from here and find the antiderivative. That's fine to write it like that. If I would like to, if this were plus or minus this. So actually, for here, yeah, this one. Welcome. You'll do it over here? Yeah. What?
So is it always the opposite?
Yeah, since U is x plus 1, we just subtracted that from both sides of the equation. And then so we have, once we put that in there, then we have
So this is like the way we're doing for that?
Yeah. Wait, so but that's not going to be 1, because that's U
Oh,
over
it's
U
all
over
just
1 half. But you have the other part. Yeah, and so the other one, this part, you can just go back. So get rid of those for that. Is that going to work? Okay, yeah, so we just simplify the powers here, or write them as a power of U. Yeah, yep.
Yellow, green, yellow, and then green, lower.
And then you just have to divide it.
I know, you want to make it pretty fast. Yeah.
Okay, so if you did it that way, so this would be a negative one, because you brought it up.
Oh, yeah, that's right.
They're their own friend. I just didn't realize they ordered bananas at the medium, so it was more. That would be.
I don't think we know, this is all like in the trial.
Okay. So once you're here, that's similar to that last problem. We now have two things over one thing, so we can split those up. We have antiderivative of u over the square root of u minus 1 over the square root of u with respect to u. We go down here. So I don't know how y'all are looking at that, but this is, you know, u over u to the 1/2. So we would just subtract their exponents. The second term is just 1 over u to the 1/2 or u to the negative 1/2. And u to the first over u to the 1/2 is u to the positive 1/2 minus u to the negative 1/2. So So we're writing them like that because we can use the power rule on both of those. So the antiderivative of u to the 1/2, we add 1 to the power, divide by the result. So we've got 2/3 u to the 3/2, or u to the 3/2 divided by 3/2, minus 2u to the 1/2. Or u to the positive 1/2 divided by 1/2. So just be mindful, you want to, once you make your substitution, you work it all the way down till after you find the antiderivative. Don't substitute in till after you found the antiderivative. And so then we just substitute back in. We've got 2/3, what was it, x plus 1, I think? Yeah, x plus 1 to the 3/2 minus 2 times x plus 1 to the 1/2. Let's see. Again, it's not, if you're unsure, you can always check, like assuming you have time left on the final, just go back to your antiderivatives and check, if I take the derivative, do I get x over root x plus 1? You might have to rewrite some of these exponents as, as roots and simplify them, but you can check your work. Okay, so are there any questions on that? Whenever you're doing a U-substitution, you've just got to basically work it down to things in terms of U that we know how to integrate, either their powers of U or their functions of U from the table in 4.9. And those are the things we can find the antiderivative of. So another substitution that'll work here is to let U equal the entire denominator. Let's let U equal to the square root of x plus 1. Now notice I can take the derivative of my substitution as it is, but it's a little bit clunky at this point because the derivative here is 1/2 times x plus 1 to the negative 1/2 dx. And I've already accounted for all of this as my u. So even though taking the derivative gives me this dx that I need to account for there, notice it adds all of this other stuff that I don't have in the integral, right? So I don't have that stuff. It would be super hard to account for that. I could multiply both sides by 2 and say 2 du is 1 over the root of x plus 1. But that doesn't really give me any more information, right? I've already accounted for 1 over the square root of x plus 1. So at that point, since the derivative is more complex than it needs to be, I guess, we'll say u is the square root of x plus 1, keeping in mind that we have to account for the x on top. We'll solve this equation for x. Okay. So now we have the x accounted for in terms of u. But notice we haven't accounted for the differential. We have to now involve the derivative. So here, let's take the derivative. I'll just write it out the long way. The derivative of u with respect to x. How do I want to write this? So we take the derivative of u squared minus 1. That gives us 2u minus 0, or 2u. And then we take the derivative of x, which is 1. So looking at that, kind of how we've been looking at it, we have 2u times du equals to dx. Is everybody okay with that? Any questions on it? Good. Okay. So that's a little bit more simple at this point when we have u squared minus 1 just equal to x to take the derivative of that relationship. Because again, that relationship u squared minus 1 equals x is the same relationship we had when we made our substitution. But it's just when we take the derivative, now we have a simpler derivative. We don't have the 1/2 x plus 1 to the negative 1/2 floating around. So then the dx here is 2u times du. So the integral x was u squared minus 1. The square root of x plus 1 was u. And then our dx was 2u du. Does anyone have any questions on where we're at? So notice from here then, this u divides that u. And I'll write it down here. What we're left with is 2 times the integral of u squared minus 1 with respect to u. So we have 2 times antiderivative u squared is u cubed over 3 minus the antiderivative of 1 with respect to u is u. Okay, let's change colors. Plus, we'll just call C1 our constant. And then resubstituting, we have 2 times the quantity u cubed, which was the square root of x plus 1 cubed over 3, minus u, the square root of x plus 1, plus this constant. And then when we multiply the 2 through, just to compare it to our previous result, we have 2/3, we have the square root of x plus 1 cubed, minus 2 times the square root of x plus 1, and then 2 times this constant just gives us another constant. So is that result the same as what we had above? Yeah, the only difference is the radical is written with a 1/2 power in our first example. Okay, it's the same thing. And honestly, on the final, things won't get that complicated, but it's good to see that, you know, certain cases where we have to solve for our substitution, certain instances where more than one U-substitution will work. I think it's important to see those. Do y'all have any questions? So now when we've talked about how to use U-substitution to find the antiderivative. Now we'll talk about when we have to compute the net area or a definite integral. Really, you've got 2 options you can take here. Just as a reminder, when we compute this integral from 0 to 2 on 1 over x plus 3 cubed, the 0 is an x value and the 2 is an x value. So you do have to keep that in mind. If you make a substitution, you also have to account for the 0 and the 2, because they're in terms of x. If we've got an integral in terms of u, we're not going to be, in general, we're not going to be going from the same bounds if we leave it in terms of u. So I suppose the first thing we might do is say, well, let's let u equal to x plus 3. So then the du, the derivative, is 1 times dx. Or 1 rather. So then we turn this into the integral of 1 over u cubed, or u to the negative 3. And so here you have two options. You either need to find the new bounds in terms of u, or you can find the antiderivative of that, resubstitute back for x, and then use the original 0 to 2 once we're dealing with x. Does that make sense?
Do we do it even stuff today?
Yeah, yeah. So notice here, if I want to stay in terms of u, which if you're doing a definite integral, I think it's easier always to stay in terms of u instead of resubstituting and using the original bounds, because the original, or sorry, the antiderivative in terms of x is just going to be a little bit more complicated than it is with u. So notice here, if u is x plus 3, we're using that to get our bounds. If u is x plus 3, when x is equal to 0, u is equal to 0 plus 3, which is 3. Okay. So for x equal to 0, which was the lower limit of integration in terms of x, in terms of u, now we're going to use 3. And when x was the upper limit, when x is 2, u is equal to 2 plus 3, which is 5. So if we're going to stick with our integral of u, we have to use the bounds 3 to 5. So that's, let me just mark this. This is one option.
Is this what you prefer?
I don't have a preference. It's always easier to use your substitution because it's easier. It's more simple than the original. Or 2, we can say from this point, I'm not going to put any bounds in yet because I know my original bounds on x were from 0 to 2. So I would first find the antiderivative of this. Then I would resubstitute. So now that I have it back, the antiderivative back in terms of x, then I can evaluate that from 0 to 2.
Otherwise, you would do what with your 3 and 5?
Otherwise, we would just stop here, find the antiderivative, plug that into the plug 3 and 5 into the antiderivative.
So we would plug 3 and 5 into pretty much negative half u to the negative 2.
Yeah.
And then do 5 minus 3,
Right.
basically.
Yep. So if we put those side by side, u to the negative 2 over negative 2, evaluated from 3 to 5. So really, both of these represent the same net area. It's just you've got to pick which path you're going to take.
They would both give you the same answer, though?
Both would give you the same answer. So you either have to use this one in terms of the original variable, or we evaluate this one. Is everybody clear on that? If you're sticking with u, 90% 95% of the time, unless it's just like this perfect match of a function, your bounds will not be the same. And so since this one doesn't have a +3 involved, yeah, the bounds are a little bit more, I guess the bounds are larger, but we don't have a +3 here. So I think it's easier to work with the U. And if you have a more complicated substitution or more complicated function that you started with finding the antiderivative of, it'll be easier to leave things in terms of U. Okay, so we'll start here. The -1/2 is the constant. We'll take that out. And then we have U to the -2 evaluated at 5. So we have 5 to the -2 minus 3 to the -2. So negative powers, we have that -1/2. This is going to be 1 over 25 minus 1 over 9, all times -1/2. Common denominator, etc. We've got 8 over 225. Do you have questions on that? If you want to do the -1/2 x plus 3 to the -2 from 0 to 2, just calculate that. Just to verify, you will get the same answer. So just since we're talking about it, I'm going to skip to this figure on the last page. This is it's sort of a more simplistic case, but it gives you I guess a visual sense of what happens when we make a U-substitution. So instead of finding the net area on 2 times 2x plus 1 from 0 to 2, looking at that particular net area, once we make a substitution, U equals 2x plus 1, then we just have the antiderivative of U from 1 to 5. So we get the line, y equals to U from a different bound 1 to 5. But we're saying that area, R prime, is the same as the area of capital R. So this was, a simple example because both integrands here are linear in terms of x, in terms of U. But if you remember one of the examples, I think it was example 2, where we had cosine cubed times sine. And after we made our U-substitution, we said that was equivalent to, what was it, negative U cubed du. So you can see a much simpler kind of thing if now we put these bounds. Let's say we go from, 0 to pi. Okay, so we say instead of finding the net area under this figure, what was U? U was cosine. And x equals 0, cosine. Sorry. Should figure out the balance. Instead of finding the net area between the x-axis and the red curve, which is the cosine cubed sine x, we can find the area from -1 to 1 on the x cubed function. I think that was example 2. If you want to reference back to that example, you'll see. Let me make sure that was correct. No, sorry. It was on example 2 on page 5. So that's another instance of U-substitution. Working with the U-substitution is a little bit more, I think it's a little bit easier. So we're saying that this area from here to here is equivalent to this area on this function. Again, much more difficult function in red than we have after we made a U-substitution. So anyhow, does that help? That's kind of, if you wanted to visualize what you're doing with the U-substitution definite integrals, that's what you're doing. Okay. So let's look at one more of those. Our integrand is x squared e to the x cubed. What would our U-substitution be? X to the third. And what are you basing that off of?
Or past examples.
Yeah, right. Remember the classic approach when using, or the classic setup when using U-substitution is that you have the product of two functions, but not only do you have the product, one of the factors is actually a variation of the derivative of the other factor. So if we know that the x cubed's derivative is 2x squared, that's giving us a clear indication as to why we should let u be x cubed, because kind of a constant times its derivative is sitting right there. So u is x cubed, du is 3x squared dx. And again, we don't have a 3 in the original integral. We have the x squared and the dx. So we want to move this 3 to the other side. So our substitution then turns the original integral into what?
0 to 8.
0 to 8. What do y'all think? Is that how our balance would change? So we're basing it off of this one here. If u is x cubed, our lower limit of integration originally was x equals to 0. Which means u is 0. And when our upper limit, when x is 2, u is 2 squared. Or sorry, 2 cubed, which is 8. Any questions on that? Okay, so what else are we looking at? The integral from 0 to 8?
And e to the u, du.
Say that again?
E to the u, du.
E to the u, du.
And then you have to have a 1 over 3.
Right, so the 1/3 is attached to the du. So we have our 1/3 du. 1/3 du gave us our x squared dx, and this e to the x cubed is now e to the u. Okay, so compute the antiderivative. We got our 1/3 antiderivative of e to the u is e to the u, evaluated from 0 to 8. So you can leave the 1/3 out of the computation because this is now a u value. 1/3 doesn't involve a u. So we can leave it out, or we could just attach it as it is. It's all the same. So we have capital F of b, e to the 8, minus capital F of a, e to the 0.
So would it just be 1/3 e to the 8 minus 1?
1/3. Yeah, because this is
you're
1, yeah.
Writing it as
So, if you're carrying if we're carrying the 1/3 through, we would have 1/3 e to the 8th minus 1/3 e to the 0. And just be careful, it's e to the 0 is 1, doesn't mean the 1/3 goes away. So these are the same thing. And then we'll just leave it as an exact answer. So that's how you handle a definite integral with a substitution. Do y'all have any questions? Any of that? Two other integrals that U-Substitution can help with. If you do go on to Calc 2, these are quite common to find the antiderivative of sine squared and cosine squared. And really, I don't think that it's necessarily U-Substitution that helps us evaluate these integrals. The key to evaluating sine squared or cosine squared is based off of the identities. Forgot exactly their name, but sine squared of x, rewriting that as 1/2 times 1 minus cosine of 2x. I think that's really the key to evaluate those. And cosine squared is 1/2 times 1 plus cosine of 2x. That's kind of similar. We have we're going to take the antiderivative of this representation of sine squared instead. Okay, that 1/2. I think usually when you see this this identity, it's 1/2 minus cosine 2x over 2. I don't know if that's how it's commonly written, but I think if we're finding the antiderivative, it's more beneficial to write it as 1/2 times that quantity, because the 1/2 is a constant of integration. Comes out here. We can find the antiderivative of 1 with respect to x and the antiderivative of cosine 2x with respect to x. So here, to find the antiderivative of cosine 2x, if you need to use a U-substitution, then u is 2x. But hopefully you just remember the one from 4.9. It's more efficient if you don't have to view those by U-substitution. So we have our 1/2. Do this. We have the 1/2 times the antiderivative of 1 with respect to x minus 1/2 antiderivative of cosine 2x with respect to x. So basically we're just distributing those three things, those three symbols out that aren't in the parentheses into the parentheses. So the antiderivative of 1/2 sorry, 1/2 times the antiderivative of dx is what?
X.
Yeah. So we have 1/2 times x. We have our minus 1/2 here. What is the antiderivative of the cosine of 2x?
1/2 sine 2x.
Right, good. It's 1 over a sine of ax. So it's 1/2 minus 1/4 sine 2x is the antiderivative of sine squared. And cosines is similar. Cosine squared is similar. So like I said, I think it's easier just to remember that it's 1 over a sine of ax as the antiderivative. Otherwise, here then your u is equal to 2x. du is 2 dx. Okay. So that's where this 1/2 would come from. If you did a u substitution, that 1/2 would give you that 1/2. Any questions on this example? I think that's it. Yeah, that's it. All right, we will take a break and then look at. Okay, so 6.2 is dealing with regions between curves. Up to this point, we've looked at Riemann sums, which deal with, or which have dealt with, a function kind of like what's the net area from A to B under this function in the x-axis. So in 6.2, what we're going to look at is regions that are bound between or by two curves instead of just the function and the axis. So just remember here what we did was we said in order to get this sum formula here, we looked at our rectangles. And we said here the thickness was some delta x. But the height of the rectangle was determined by, wherever we chose to evaluate the rectangle at. Okay, and we called that our x star. So k was the height of the, what we'll say, the kth rectangle. Sorry, they're using x bar here, sorry. This is x star. So I just want to point out at this point, though, that when we computed, since we're always talking about in the previous sections, the function to the axis, that gave us that distance. Okay, so we said whatever this y value is here, this is our f of x star sub k as a y value. We said that's just the height because it's on the x-axis. We know this y value is 0. So really measuring that height, it's the distance from that y value to 0. And this will help us when we look at how it's formulated here in 6.2. But this is the same thing as saying the integral from a to b on f of x minus 0 dx. So in the previous section, that sort of that lower boundary to determine the height of each rectangle was always 0. So we didn't really worry about it. In 6.2, we have a more generic region. So like we have our f of x there, and then maybe we have this other function g of x like this. And we want to know what is that area that's bound by the function f and g from a to b. So what do you think changes here? I'll give you a hint. We still slice this region up. We still look at rectangles, and we take that sum as the number of rectangles goes to infinity. However, what is now the height of this rectangle? The base is still, we're going to call delta x. But how do we measure the height of that rectangle now?
F of x minus g of x.
Yeah, the height of this rectangle is now f of x minus g of x. I just put a specific number here. What if f of x were 7 and g of x were 3? How do we measure that height? We just say it's 7 minus 3. Is everybody okay with that? So the height of each rectangle, we'll keep it consistent with our previous notation. The height of the kth rectangle is f of x star sub k minus g of x star sub k. In other words, to find that area bound by f of x and g of x, or on the interval AB, we have to compute the integral from a to b of f of x minus g of x times dx. So again, think about each one of these for every x value as the height of each rectangle. Our dx was the width of each rectangle. And I'll make the note if g of x is equal to 0, this is from, then what we're doing is just computing in that area from chapter 5. Here we're looking at a more general region. Okay, does that make sense? Does anyone have any questions on that conceptually? All right, one other thing that we see here in this section, it's based on the same idea, but maybe we have instead like a function of y. let's call this h of y. And we'll call this j of y. We can do exactly what we've been doing with x, but we can do that with respect to y. The only thing is we're sort of shifting our perspective. So here now the rectangles would run like this. They would have some thickness delta y, or width, I guess. And the height of the rectangle would be what?
Y star K.
Kind of. But notice here when we're looking at this in terms of x, and we wanted to know what was the height, we were saying what is the height of this rectangle that goes from 7 to 3, for instance. Right, that's the height of the rectangle. Now to measure the height of the rectangle, we're asking what is this height? What is that distance?
B minus A?
If this were A and this were B, that would be correct. So, you know, again, if this were 7 and this were 3, how do we measure that height or that length right there that corresponds to the height of a rectangle? It's just the right minus the left. So here we take the right function minus the left function. I guess we can go ahead and just put y in here. So when you're in this situation where you're integrating with respect to y, the height of each rectangle, you can think about it as it's the right function minus the left function. Let's put bounds on y. Say that's a y value of c, and this is a y value of d. So we can say that the area is the integral from c to d of the right function minus the left function with respect to y. Right minus left in terms of y. And so then maybe think about the ones in terms of x as the top minus the bottom. The height of each rectangle is the top function minus the bottom. The height. Top function minus bottom with respect to x, because your rectangles are vertical. Right minus left with respect to y, because your rectangles are horizontal. So hopefully that is anything that's mysterious or mystical. It's just, you know, in the sense of x, we have the rectangles running like this. You know, just turn your head sideways, and we can do that with y. That's pretty much all it is. Okay. So let's look at some examples to see how that actually works. Find the area of the region between y equals x cubed, y equals x squared minus x on the interval from 0 to 1. So here's an x value of 0. Just going to highlight these. This is our x cubed. Oh wait, that should be, yeah, that's x cubed. Y equals x cubed. And then the blue is our quadratic. So it says from 0 to 1 in between those two curves. Here's an x value of 1. So what we're after is this area here. After that area. And I'll just kind of redraw this so it's a little bit larger over here. Okay, so we're finding the area of that region. We know that this is an x value of 0 and that this is an x value of 1. So we have the bounds for the integral. The integral goes from an x value of 0 to an x value of 1. Just because it specifies to look at that region on 0, 1, notice if we looked at that region from like 0 to 2, then there's more area to consider. But since we're stopping at 1, then we're not considering that area that's after that. So integral from 0 to 1, and then what would the function or the integrand look like to calculate that region? So if I just drew one of these rectangles in here, let's say this is one rectangle. What's the height of each rectangle that fills up this region? What's the height of each rectangle determined by, I should say?
Is it the two functions? So
You're right.
x to the third minus x squared minus x.
Yeah, exactly. The height of this rectangle is simply the top coordinate location minus the bottom. But all of those vary, right? The height of this rectangle is certainly different than the height of that rectangle. But nonetheless, the height of that rectangle on the far left is still the top value minus the bottom value. So we have the top minus the bottom with respect to x. Are there any questions on that setup? Does that make sense to y'all? Are we doing that? Another thing that you have to consider is if I fill this region, that's why it's good to visualize these regions. If I fill this region up with all of these rectangles, does the top minus the bottom ever change? In other words, for all of those rectangles that fill up that region, is the top function always x squared and the bottom function always x cubed and the bottom function always x squared minus x? Yeah. From start to finish, it's always x cubed minus x squared minus x. Okay, so in order to integrate this, we're just going to combine what we can combine, if anything, and then use our power rule here. So we have x cubed minus x squared plus x, which we can use the power rule on all of those. So we have x to the fourth over 4 minus x cubed over 3 plus x squared over 2, evaluated from 0 to 1. bounds are pretty easy. So we've got f of b, 1/4 minus 1/3 plus a half, minus f of a, which is 0 over 4 minus 0 over 3 plus 0 over 2. So that's 5/12 minus 0 or 5/12. Okay, so that's kind of secondary. The setup, anybody have any questions on the setup? So in this, our bounds were actually given to us. Oftentimes you do have to find the bounds yourself. So consider the curves 8 over x squared, which is the thing in red. I don't know if y'all's printed out in color or not. So that's my 8 over x squared. Y is 8x, so that's in blue. And y equals to x. So it says find the area of the region bounded by those three things. So we're looking for the sometimes it's a point of confusion as to which area we're actually finding. Okay, so this area here down below, are we finding that area? No, why not?
It's not bounded by all three.
Right, because it's only bound, the area in black is bound by y equals x, the x-axis, and 8 over x squared. So you want the region, or the area rather, that's bound by all three curves. So we're finding this area right here. And once again, I'm going to redraw this just so it's a little bit more exaggerated or blown up here. So that's the region we're finding the area of. So really, I guess the first piece is just identify what you're finding the area of. Then if we're integrating with respect to x, we have to ask ourselves, if I fill this region up with these rectangles, does the top minus the bottom ever change? Yeah, so one part, the top is 8x minus x, top minus bottom is 8x minus x. But then when we get over here, it's now the top is 8 over x squared minus x. So hopefully you can see at this point, or this x value rather, once we cross that threshold, then the top minus the bottom, or the height of the rectangles, now are defined differently. Does everybody see that? So what this is equivalent to, if I can draw this over here. Maybe I'll do this. What that's equivalent to is finding the area of that region plus the area of the other region. Oh, dang it. Why did that change? So we have to actually add those two areas up. Since the top and bottom are changing. So maybe you can look at this graph and say, well, I know this intersection point here has an x value of 0. But what are the other intersection points? In other words, what is this intersection point? This is x equals to what? And this one over here, let me do this in a different color. This point over here is x equal to what? So let me do this one in this color. X equals to what there? Corresponds to that point. Yeah? And x equals to what here corresponds to that point. So you've got to find those 2 points, otherwise you won't have the correct area. So let's find the points of intersection. So that point in blue, that was where the blue line equals the red line. That's where those two things intersect. So that point is defined by when 8x equals 8 over x squared. So when does 8x equal 8 over x squared? Clear the fraction, multiply through by x squared. We have 8x cubed equals to 8. So that happens when x cubed is equal to 1. That happens when x is equal to 1. So we know that this value here occurs at x equal to 1. And this is the same line, so this is also x equal to 1 here. We just kind of separated those two different regions. Okay. Is everybody all right with what we've done? Are there any questions? Second point of intersection, how do we find the, well, whatever that pink color, how do we find that intersection?
X is equal to 8 over x squared.
Yeah. So that point of intersection is where the red intersects the purple, which is where 8 over x squared is equal to x. Same method to solve, multiply through by x squared. So we have 8 equals x cubed, which means x is equal to 2. So that's an x value of 2. Any questions on that? So let's set up the areas for each one of those particular figures. The blue and the purple, what am I going to look at? It's the integral from where to where? Zero to one. What's the function or the height of each rectangle? I mean, well, yeah, the height, again, since the rectangles run like this, the height is just defined as the top minus the bottom. You're just measuring that vertical distance. So the height is the blue function minus the purple function. The height of all of those rectangles are defined by 8x minus x dx. And so that's the area of that figure on the left, and then we have to add to that the figure on the right, which we go from where to where? The integral from
1 to 2.
1 to 2. Again, rectangles are vertical. Distance, or height, if you will, is the top minus the bottom. 8 over x squared minus x. dx. So this is what we have to compute in order to compute that area. Does anyone have any questions? I'll just do this on the bottom here. So I'm just gonna scoot this down. Notice the first one we can combine like terms. It's the integral from 0 to 1, 8x minus x. So it's just the integral of 0 to 1 of 7x plus the integral from 1 to 2 of 8 over x squared minus x. We can't combine the terms there, but we can integrate each term or find the antiderivative of each term. So we'll do the first one, the antiderivative of 7x with respect to x is 7x squared over 2. And keep in mind we're evaluating that from 0 to 1. Plus, what's the antiderivative of 8 over x squared? You want to view that as a power. So what's the antiderivative of 8 times x to the negative 2? Negative 8 over x, right? Because we'll have 8 times x to the negative 1 divided by negative 1. So that'll give us negative 8 times x to the negative 1. And the antiderivative of x is x squared over 2. But we're evaluating this function or this antiderivative from 1 to 2. So we have, I'll just write this out. This is 7 times 1 squared over 2 minus 7 times 0 squared over 2 for the first one, plus, so get all of this in here. Evaluated at 2, we have negative 8 1 minus 2 squared over 2. So that's that antiderivative at b minus 8 times 1 to the negative 1 minus 1 squared over 2. Nice, huh? So that's really the gist of it, I think. Adding these fractions, subtracting them, whatever, it's really not a concern, I think. Does anyone have any questions on how we set this up? It's the same thing we were doing in chapter 5, but now you've got another layer of complexity. And it is a lot more complex. Well, if something doesn't sit right with you, please email me. So we combine all of that stuff to get 6. Any questions on that example? Okay, we'll look at one more. So this one we're going to integrate with respect to y. Let me just highlight these curves here. And it says we've got these two curves, functions of y, from a y value of -2 to a y value of +2. And I don't know if you might not be able to see that on your printout, but here's a y value of -2, and here's our y value of 2. So they've already given us the bounds. We're finding this area here, finding all of that area. Let me label these. Top curve, I guess, well, red curve is y cubed minus 4y. And then this orangish one is the other one. Y cubed plus y squared plus 8 is x. So notice why this one would be difficult, not impossible, but extremely difficult if we were using or integrating with respect to x. If we had to integrate with respect to x, then our rectangles have to run in this direction. So I have all of these rectangles, right? If I were integrating this with respect to x, then my rectangles have to be in that direction. But notice, like, even for this first one here on the left that we drew, we would say, well, the top and the bottom are defined by the same function. It's a little bit misleading because if I want to know what the top is and what the bottom is here and here, then I have to express this function y cubed minus 4y in terms of x. In other words, that I would have to solve both of these equations for x, or y rather. Solve for y for both of these, right? Because if I'm doing this with respect to x, we've always seen y equals to, sine of x, or the square root of x squared plus 1, or They've all been functions of x if we're integrating with respect to x. So that's one challenge. You've got a cubic equation you've got to solve for y for, not an easy thing to do. And then that's really the gist of why we would want to integrate this with respect to y, because we don't want to have to solve for y in both of those functions. So if I can integrate this with respect to y, I don't even have to worry about solving for x, or y rather. I'm integrating with respect to y, I just have to look at my rectangles filling up the region like this, and asking myself, in this instance, how do I determine the height of each rectangle? If it's weird to think about that as the height, how do I determine the length of each rectangle? The right minus the left. So does the right minus the left ever change? No, it's always the same. It's always orange minus red. I'm just going to exaggerate one of these rectangles a little bit, just so we're a little bit more clear on what we're doing. So here's this rectangle. Notice now the length, or the height, if you will, is defined by right minus the left. But now the thickness of each rectangle is not a measurement, or is not a distance in the x direction. It's now a distance in the y direction. So that is, we're integrating with respect to y. And that kind of determines it. How do your rectangles you're filling the region up with run? Left to right, up and down. That determines integration with respect to x or with respect to y. So we're given that the y values go from -2 to 2. The function we're looking at, determining the height, we said in this scenario is always right minus left. So there's the right. Minus the left with respect to y. So that setup there gives us that area in terms of y, or with respect to y. Are there any questions on that? So if you were able to solve for y here, like for instance this red curve, it actually consists of 3 different functions of x. So like, maybe this part of the curve is one function of x, this part of the curve is another function of x, and this part of the curve is the third function of x. It's a really difficult thing to do. But here, the area defined this way, we can collect our like terms and integrate powers. So I have y cubed minus y cubed, that's gone. Y squared stays. Positive 4y stays. And positive 8 stays. So what do we have? Y cubed over 3 plus 4y squared over 2, 2y squared plus 8y, evaluated from -2 to 2. So we'll just plug these in. 2 cubed over 3 plus 2 times 2 squared plus 8 times 2 minus 2 cubed over 3 plus 2 times -2 squared plus 8 times negative 2. It's 112 over 3. Questions on that example?
On the test, will we be getting the graphs?
Yeah, on the test I'll give you the graphs, I won't give you the intersection points. The final's actually out of 116 points. I'll just circle the number of questions like this. So you'll have 5 questions that are short answer. Okay, and like, you know, question, for example, what's the derivative with respect to x of the integral from a to x of, I don't know, sine t dt? Something like that. In theory, you should be able to answer pretty quickly. By the way, what is the answer there?
Sin X.
Sine x, good. Okay, there's one question where you have to find the net area using the definition. So evaluate a definite integral. Using the definition, which is the limit of the sum definition. So we use this one. Our x star was the right Riemann sum, so that was a plus k delta x times delta x.
What would be pretty simple where we can do like k equals n minus, or n plus n, whatever, you know, do you know what I'm talking about? Where it's like k squared equals n.
Oh, the summation formulas from 5.1 where the sum of k squared
You
is.
don't have like the summation calculator.
No, you won't have this, but you don't need the summation calculator. In fact, using the definition, that a separate handout I called 5.1 part 2, you could use that theorem, which is much more efficient to do these. Do you remember that? You have a handout, handouts on D2L. I think it's the same title, Theorem 5.1 Part 2. So what that means is if it says you have to evaluate the integral from 3 to 7 of, I don't know, x squared dx, you've got to turn all of that into this right here. The limit as n goes to infinity. You can't, if you want to check, you can compute it the short way, but you do have to use the definition to evaluate that. There are going to be 3 limits. And again, super helpful in a lot of instances, to know L'Hopital's rule. We also had, I think in particular, where we were approaching a vertical asymptote. This was in 4.7. So we call those infinite limits. From, I don't remember, that was either 2.4 or 2.5. There's going to be one question we have to, where you're given a piecewise function. Find specified limits. Oops. So that was, we had a similar exam question on exam 1. And just for reference example, if you were given f of x equals to x plus 1 for x less than 1 and x squared plus 4 for x larger than or equal to 1, evaluate certain limits on something like that. So that was exam 1 question. You'll have one question where you have to find the equation of a tangent line at a given point. Equation of the tangent line at the given point. There's going to be 6 derivatives. So, product rule, quotient rule, chain rule, derivatives, logarithms, exponentials. Again, that's something you can have on your note card, which hopefully you already have a decent amount of stuff. There's going to be, in addition, kind of subcategory, there's one log differentiation. And then there's one in here as well for implicit differentiation. You'll have one question where you're given a function f, the derivative f prime, and the function's second derivative, and then you'll be given that information. What you need to find is the intervals of increasing and decreasing. Any local max or mins. Intervals of concavity. And inflection points. I'm going to start a new page. Does Do y'all have what you need from this?
Can you scoot up for a minute?
Mm-hmm.
A little more to the given f of x and a point.
On the equation of the
yeah,
tangent
that's all I
line?
need. You're good.
Okay. There's going to be 4 antiderivatives. Some of those could involve U-substitution. There's 2 definite integrals. Remember, another word for the antiderivative was the indefinite integral. So, all of those could involve a U-substitution. One question from 5.4 to find the average value. So you're given f of x on some closed interval. Find the average value. Which was defined as f bar. And just so you remember, f bar is 1 over b minus a times the net area from a to b. Let's get that down. Remember, you cannot have any Chapter 5 stuff on your note card, so that's from Chapter 5. You need to remember that formula. You have to hand in your note card after the exam. So I would recommend that you don't scratch anything out or mark anything out, because if you hand in a note card that has stuff marked out on it, then it's super suspicious, right? There's no way I didn't know what you marked out. Could have been Chapter 5 stuff. So if you do mark something out on your note card, just please show me before the exam. Like, hey, I had to mark this out because I made a mistake. If you hand in a note card that's marked out after the exam without showing me, I'm going to assume that you cheated. Okay, that's about the only way I can police those things. There's one question where you have to find position, velocity, and acceleration. And one question from 6.2. Find the area of the region of a region bound. By 2 or more functions. That's from 6.2. So the graph will be given. Graph will be given. Points of intersection, you might have to find. They might be really easy. You should know how to find them though. I won't give you anything crazy to have to solve to find the points of intersection if you have to do so. And that's it. Yeah.
Do you know how much like each question is weighted?
Yeah,
which ones are
but
weighted more than-
I don't have that offhand. Yeah. Okay, yeah.
I know you said you can't have like worked problems on the note card. Can you have like bullet points saying like first do this, second
Yeah.
do this? Okay.
Yeah, you can totally write down steps or processes like logarithmic differentiation. First, take the log of both sides, simplify the one side with properties of logarithms. Here's the properties of logarithms. Then take the derivative of both sides.
Okay.
Yeah.
Cool.
And then even, since we covered that, you could even say that, if you have to take the derivative of both sides, that this is y prime over y, you can have stuff like that.
Okay.
You just can't have a particular example worked out. Yeah, do y'all have any other questions?
How big can you card these?
3-inch by 5-inch note card, please. If you have any other questions about the note card or content, then please let me know.